Hello everyone, I am Esat Kalfaoglu. I am from Middle East Technical University, Ankara, Turkey. Today I'm going to present vision-based lighting state detection and curtain openness ratio prediction. For my presentation, I will start with introduction part. Then I present the experimental setup of our work. Then I present methods for our problems, which are basically light state detection and curtain openness ratio prediction. And at the end, I will conclude my presentation. There are two problems covered in our work. The first one is light state detection, which is predicting whether the artificial light is on or off for a given time instant from a video. The second one is curtain openness ratio prediction, which is estimating the portion of window that is not covered by the shading devices and mostly curtains for a given time instance from a video. In other words, estimating the portion of window from which the daylight can enter. So, why are the light state detection and curtain openness ratio prediction important? Firstly, the estimated values of both tasks can be utilized in the energy modeling of existing buildings as an alternative to the standard schedule templates. The increased precision in these schedules have the potential to increase the precision of simulation results and leads to better informed energy analysis of existing buildings. Secondly, it is beneficial to discover the correlation between the lighting and the shading, which is helpful in identifying the unnecessary utilization of lighting when the curtains are drawn. The environment of our experimental setup is a classroom from the architecture department of Middle East Technical University. You can see the plan of the classroom on the left and the camera field of view of the classroom on the right. As seen in the plan, there are 6 light sources from L1 to L6, but 4 of them, L2, L3, L4 and L5 are in the camera field of view and their area of them are represented as green rectangular boxes in the right figure. There are 2 switches, S1 and S2, and L2 and L4 are connected to S1 and L3 and L5 are connected to S2. There is also a big green box on the right figure to indicate the ceiling region of the classroom. Additionally, window region is clearly visible in the camera field of view. There are 2 methods proposed to predict the light states. Both of them depends on capturing the light state changes instead of estimating the light states directly. And these changes basically are the instances of turning the light on or off. 2 proposed methods are called detection via local illumination change or local method and global illumination change or global method. Local method assumes light source locations are known. To capture the change, the method benefits from the first order derivative because when the light is turned on, the average intensity of the area of light sources increases or vice versa. On the other hand, global method assumes that the light source locations are not known and only the ceiling area is given to the system. Global method tries to benefit from the exposure change. To make it clear, when there is a change in the light of the environment, the camera still tries to make the average intensity constant to present a better image. For example, when the light is turned on, the average intensity in the global image first increases but then decreases because of the camera exposure response. Therefore, because there is a two-directional change, not only it benefits from the first order derivative, but also the second order derivative. The advantage of global method is there is no need to label all the light sources. It might even be utilized without the scaling information. However, the method is more prone to false alarms compared to local methods. In order to deal with the problem, the information from the video needs to be converted to 1D signal. Consider a video which consists of n number of frames from f1 to fn. Firstly, the average pixel intensity of related regions are calculated for every frame. These regions are basically the average pixel intensity of light sources L2, L3, L4 and L5 for the local method, or the average pixel intensity of the ceiling region for the global method. Then, by combining all the average pixel intensity information of frames, 1D signal is created. Local method is a 3 steps algorithm. In the first step, obtained 1D signal is convolved with Gaussian filter in order to reduce the noise. Secondly, the first order derivative is calculated by convolving with filter f. Then, the peak and depth of the resulting filter is calculated and the threshold is applied. There are 2 options for local method. The first option is single switch, where all light sources are connected to single switch. The second option is multiple switch, in which light sources are connected to their own switches. In multiple switch, the requirement is needed that both switches should be triggered in order to reduce the false alarms. Global method is a four-steps algorithm. In the first step, the mean is extracted from the signal. In the second step, Laplacian of Gaussian. Log filter is applied in order to find the region of exposure change. The shape of log filter is like a Mexican hat, sombrero. Then, the peaks and dips are found and the threshold is applied similar to the local method. Additionally, the exposure blobs should have zero crossings in the first order derivative. Therefore, blobs without zero crossings are eliminated at the final step. There are some false alarm problems, such as immediate daylight change and projector light change, which especially worsen the performance of global method. Background modeling is one of the ways to eliminate this kind of false alarms. The idea is that if there is a change in light states, there should be a foreground part, basically a hand, around the switch location. In the A part of the figure, there is a person who is about to turn on the lights, and in the B and C part of the figure, you can see the background modeling of whole image and the switch location respectively. Foreground parts are shown as white in the figure. For background modeling, mixture of Gaussian 2 Mach 2 algorithm is utilized. The negative aspect of both of the proposed methods is that they try to detect the state changes, not the state itself. As a consequence, the error in detection propagates in time. To mitigate this problem, we consider that using the light sensor on the camera might be helpful if switching of cases are missed by the proposed methods. The beneficial side of the sensor is that there is a possible threshold value such that we can be sure that the light sources are not lighting under that threshold. For the results, two 1-week recordings from the experimental setup are used. Precision, recall, F1 score are commonly used metrics, and these metrics help us how much methods are successful in detecting the state changes. Correctness is a metric that we have defined for the problem, and it is to measure directly the correctness of light states instead of the changes of the light states. On the left table, the results of the 1-week March 2019 dataset is shown. From the correctness perspective, the best method is local method with multiple switch settings. For the other metrics, the best method is global with MOG, or so to say, global with background modeling. It should be highlighted that the addition of background modeling has increased the performance significantly. On the right table, the performance of global method with background modeling is shown without and with sensor fusion on two 1-week dataset, December 2018 and March 2019. The performance increase with sensor fusion is dramatic, especially in December 2018. For curtain openness ratio prediction task, the proposed algorithm consists of three stages. In the figure 3, these stages are shown. In the A part of the figure, the input image is shown. You can observe the blue curtain and the open part of the window. The first stage of the proposed method is background modeling, in which the foregrounds are removed to some extent as seen in the B part of the figure. The second stage is binarization, or thresholding, and the output of this stage is shown in the C part of the figure. Then, with the morphology operation at the final stage, the imperfections and the occluding objects are removed as shown in the D part of the figure. For error calculation to evaluate the performance, 18 time instances from 1-week video recordings are selected randomly. The open regions of window for all instances are manually labeled. The average error from the all selected instances is calculated as 2.55%. To conclude, light state detection and curtain openness ratio prediction tasks from visual data are studied. The proposed methods for both tasks are obtained some satisfactory results, considering that these are hitherto unaddressed area in the literature. Thank you for listening.